Here's an application of vector addition, the geometry of parallelepipeds. We have a parallelepiped in 3 space. We'll assume we have a vertex at the origin, and at the origin we have 3 edges given by the vectors u, v, and w. If we sketch these vectors in 3 space, our picture looks like this. Then we can complete our vectors to a parallelepiped to get this picture here. So note the vector w is running along the back. Question: find the lengths of the 4 diagonals. Now, our technique is going to be to write each diagonal as a linear combination of u, v, and w. Then we'll just take the length of that linear combination. Now, to start, if I look for the diagonal that runs from the origin to its opposite vertex, how do I represent that opposite vertex as a sum of u, v, and w? Okay, well, let's draw a parallelepiped with right angles. That won't affect how the addition works, it just affects the picture. Now, how do I add vectors? So the idea is, geometrically, we line our vectors up heel to toe, and then we just draw the line in from our start point to our end point to get our new vector. So for instance, if I want to go to this vertex, which is opposite the origin, I take u plus v plus w. Okay, so if we draw in u, I want to add v to that, so we just take, okay, we're going heel to toe, so I take the heel of v, put it at the toe of u, and then just draw it in. Then likewise for w. So you note when we add these 3 together, we land on the opposite vertex. Then I just want to take the length of this vector here to get the length of the diagonal. So if we were in the case where, okay, we had a rectangular parallelepiped, so say we had edges, okay, given by u, v, and w. Our opposite vertex from the origin is just given by the sum. And then if I take the length of this vector here, we get, okay, we take the sum of the squares, take the square root, so I get a square root of 50. Now, we don't have the right angle, not a problem, we just use the same formula. So I take the sum of u, v, and w. Okay, that's going to give me 4, 5, 1. Then we just take the length. So it's going to give me 16 plus 25 plus 1. We take the square root. We get a square root of 42 for the length of our first diagonal. Now, how about the other diagonals? The problem we have, if I consider opposite vertices, neither of those vertices are going to be the origin. Now, that won't be a problem because of the way vector addition works. Let's note, if I consider this vertex here and its opposite, well, by vector addition, we have that this vertex can be represented as the vector u plus v. The opposite is just going to be the vector w. So if I want to consider the vector that joins u plus v to w, what do? We're not based at the origin. If I wanted to make a vector that was based at the origin, we would just take the difference, slide it over. So this diagonal here can be represented as the vector u plus v minus w, or it's negative, depending on what direction we want to go in. Here we only care about the length, so the direction isn't going to be important, so I can use plus or minus. If I take the length of u plus v minus w, okay, so we have u plus v minus w, that gives us the vector 0, 1, 1. I take its length, and we get square root of 2. Now, for the other 2 diagonals, same procedure, we just change the order of the u, v, and w. So we'll have u, w, and v, and v, w, and u. When we work those out, we get a square root of 14 and a square root of 22. So the lengths of our 4 diagonals are going to be square root of 2, square root of 14, square root of 22, and square root of 42.